Good question. I don't know if someone else.
This is more of a general question. I'm curious how, if you have experienced this before, like how do you come up with, how do you recognize this problem?
How do I recognise the problem? To be honest with you, I didn't actually have any experience in this before. I just was researching problems of this sort. And I found the Hugh et al. Paper actually, and I saw that it was so recent, and I kind of was a bit surprised actually that someone hadn't done this previously. And so therefore I thought maybe this is something that needs to be kind of addressed. And obviously it's quite an important issue, especially with so much use of artificial intelligence now, like especially for important decisions such as like in healthcare, that sort of thing. So I thought that it's something that needs to be addressed.
So it seems like a very important issue.
Yeah, that's what I thought.
I feel like when you're talking about issues of fairness,
Yes.
that comes up like who's responsible, and like in this framework, who do you think is like the responsible party for ensuring fairness?
Yeah, it's a good question. I think essentially, well, obviously this framework, it puts a lot of decisions up to the developer themselves, whoever's developing the model for whatever use it's going to be used for. So I think probably in this scenario, it would be down to them. But a lot is sort of left up to their discretion. And so they can adjust certain parameters based on whatever use case, whether it's for hiring, whether it's for healthcare, whatever it is. And obviously you get the data plays a massive part as well, which is kind of why all the auditing is important. So yeah, cool. Thank you. Yeah, right. Any other questions?
I could guess. I find it really interesting the fact that you add an interpretability to the model, and then like I just wanted to know a little bit more about like how that would look like and what kind of explanations.
Yeah. If I go back to the slide, actually, I just ran out of time.
Okay, sorry.
So essentially, yeah, a couple of like particular examples be like rule based. So you can say that this particular example was rejected because it didn't. Because the score was higher than the threshold, for example. There's also case-based, which is essentially saying we haven't seen anything like this before, therefore it's rejected. And you can sort of use K and N to do that. There's counterfactual as well, which is introduced by Walter, 2018, I think so pronounced it, which essentially is like the minimum change for it to be accepted. So you can say like it was this far off threshold, therefore it's rejected. And then finally, there's decomposed uncertainty, which separates epistemic. So epistemic is like actual sort of uncertainty based on a lack of data, and aleatoric, which is like inherent uncertainty within the data, and it separates those two. And actually, I think that's probably the most important one, because obviously if you have persistently elevated epistemic uncertainty in one demographic group, you know that the problem is the underlying representation. So, but as I said, like before, it's completely at the discretion of the developer. These are just some sort of common ideas, essentially. But yeah.
Okay.
Yeah.
So existing approaches tend to assume closed and static label sets, where the set species is fixed prior to training. However, we argue that wildlife monitoring is fundamentally an open world detection problem, where the taxonomy of species can change and evolve over time. And this is done in various ways, maybe through the identification or discovery of a new species, or through an invasive species coming into a specific environment. And this mismatch between the static assumptions and the dynamic reality of wildlife monitoring leads to brittle systems that fail where value is the highest. And that's for rare, endangered, and newly discovered species. So I'm going to quickly run through a few of the main areas that both try to approach this problem and also justify the proposal that I've made. The first of which being object detection. So Beery in 2019 proposes a generalized wildlife detector model, and then in 2023 discusses the implementation of this model, which was called Mega Detector. and supplies several use cases of real world applications across the globe and across different natural environments. However, wildlife detection only solves the problem of identifying where animals are in images, rather than the species classification that is the main focus of labeling. Few shot approaches, especially those based on Wang et al. In 2020, which is a fine-tuning approach to few shot detection, are especially applicable to wildlife detection due to the nature of endangered species having limited data availability. And Yan et al. Implement a few shot detection based approach that showed that few shot detection is effective at combating this limited data, and that they are able to detect and identify endangered species. However, few shot approaches still require retraining of the entire model whenever a new species needs to be introduced. And this obviously is costly when done again and again. Another feature of wildlife monitoring is that it's a long tail recognition problem. And this means that the vast majority of the training set is attributed down to the few most frequent species. And this provides challenges when trying to detect species that fall on the tail of this distribution that are less common. And Sui et al. Use a reweighting scheme to address to rebalance loss, which they show to be an effective way to handle this type of long tail recognition. And this would be an effective way at combating the class imbalance problem. However, it still doesn't address when new classes need to be introduced to the feature set. And then moving on to open set and open world recognition. Open set recognition is where a model is able to identify input that doesn't fit into any of the known classes and instead identifies it as unknown. And then open world builds on open set by being able to continually learn new classes over time, detecting them as unknown. So Bendel and Volt, they propose a open set solution called Open Maps, which looks at the activations in the penultimate layer of the detecting model and sees if the activations are sufficiently far enough from known class activations to identify an unknown class. And then Joseph et al. Build on this to make it an open world approach, which is able to continually learn these unknown classes. However, even open world recognition by Joseph et al. Still requires retraining to add these unknown classes into the model once they're labeled. And so this kind of frames the gap in the literature that I've identified, which is a species classification model where the label set is able to dynamically be added to without retraining. And work on representation learning for visual similarity, as well as retrieval augmented learning, justifies the viability for my proposed solution, which uses a retrieval-based image embedding model. So my position is, like I said, a retrieval conditioned framework for open world classification for which the set of target species can change over time. By externalizing species knowledge into a non-parametric memory, our approach aims to reduce these retraining related costs, to improve accuracy for rare and endangered species, and also improve explainability through the use of retrieved visual evidence. And then we also propose a new evaluation protocol for which at the start of evaluation, specific species classes are held back and then introduced periodically to simulate an evolving environment. And so this is a visualization of the proposed classification pipeline, which starts with a class agnostic object detector, so such as the one proposed by Beery, mega detector, which outputs the cropped animal region, which then is embedded using the embedding model. So this could be something similar to the cited FaceNet or a model like DynaV2 or something like that, which outputs then this query embedding, which is used for retrieval from an external embedding database, which is our form of non-parametric memory, to retrieve the k-nearest neighbor embeddings. These nearest neighbor embeddings are then used as, they're input into the retrieval condition species classifier as context, along with the original query, to decide the final class prediction. And the interesting thing about the species classifier is that instead of having a traditional output head over the where each node in the output head is refers to one of the classes in the class set, instead each node refers to one of the k-nearest neighbor embeddings that's the input. And so it kind of works. You can almost imagine it like an attention mechanism, which means that it has an innate ability to handle this kind of long-tailed nature, because it doesn't have the frequency bias when it comes to the really common classes. The reason that we use a deep classifier model rather than just performing classification on the k-nearest neighbor embeddings is so that we can implement approach based on open maps by Bendel and Bolt, which will look at the activations in the penultimate layer of this classifier to then be able to identify whether it's an unknown input, rather than a simple thresholding on the nearest neighbor distance, which really acts more as like an uncertainty of prediction rather than a true unknown classification.
The 3 arrows in the top right corner.
Okay, hello everyone, welcome to my presentation. Today I'll be talking about knowledge augmented reinforcement learning for complex video games, specifically strategy games. So in this presentation, there are 4 sections. First, we're going to start with some project background and context. Next, we're going to go into the literature gap. And then I'm going to be talking about my position and proposal. And then finally, I'm going to be talking about the impacts of that proposal and future outlook. So first, project background. So reinforcement learning in complex games is a widely researched topic in the modern day. Some modern examples include Minow's Atari model, which was one of the pioneer models in 2013. They taught a reinforcement learning algorithm to play plethora of Atari games. So I'll start with defining a few things. By complex games, I'm talking about games which have a non-deterministic obscured reward, obscured state reward, which is hidden behind gameplay elements. So for instance, in this presentation, we're going to be talking about StarCraft 2 and Dota 2, but mainly Dota 2. And again, some context for you if you don't know what Dota 2 is. It's a 5 versus 5 multiplayer game where each player plays as a character, each of which is controlled by a mouse and keyboard, each of which can cast abilities, the goal being to destroy objectives on the map on the enemy side. So why is reinforcement learning relevant in this area? It's relevant because a lot of these games, since they're very complex, reinforcement learning can pick up strategies by doing self-play. And that's the main form of input for reinforcement learning algorithms. So reinforcement learning can manage this huge complexity, and it can learn without labels as well. And specifically for games like this, reinforcement learning algorithms have proved to learn long-term strategy as well, which is very relevant in a game that can go on for 30 to 40 minutes. And the important thing to take away is that with all things considered, self-play is the assumption for the main input to learning or reinforcement learning in complex games. So what is the state of the art? The current state of the art consists of OpenAI 5, which in 2019 was able to beat the best best team in the world, OG. And AlphaStar, OpenAI 5 plays Dota 2, and AlphaStar, which plays StarCraft 2, was able to reach the rank of Grandmaster, which is the top 1,000 players in the world in its region. However, these large models, they have a very specific characteristics between them. They all require a lot of compute time and resources in order to train. And the problem with that, well, I'll explain that later, but this is because there is a massive interaction environment for these games, where OpenAI 5 quotes in one game there can be up to 20,000 or more decisions made. And OpenAI 5 was trained over 1 million or more games. So it's a very, very, very big training space and interaction space. So why does this matter? So within my project, I defined 2 different types of games. And I realized talking about this that I kind of misnamed them, but I'll explain them. So I defined knowledge-sparse and knowledge-rich games. And knowledge-sparse games are domains where structured human knowledge does not meaningfully reduce learning costs. So for instance, in chess, you have deterministic states. And say you have a checkmate, that is also a deterministic state. If you have infinite compute, you're able to compute how from one state to another you would reach that checkmate. Whereas in a game like Dota 2, since it's state obscure, it's not completely obvious from the current state that you're in how you can reach a certain goal that you have long term. So that's why reinforcement learning, and specifically for this project, well, sorry, I should define knowledge-rich environments first. So knowledge-rich environments are domains where there's extensive accessible human knowledge, which could significantly reduce the sample complexity, making pure self-play inefficient. So the difference being, a better name I've come up with is knowledge relevant and knowledge irrelevant. Knowledge relevant and knowledge irrelevant, where if you have just the game, you'd be able to learn from just self-play. But with this game, my proposal is that self-play is highly inefficient for learning. Okay, so in modern systems, reinforcement learning performance tends to scale with compute and not knowledge. This is the trend that we're seeing. So this brings us to the gap. So within my research, I found 3 clear gaps, those being knowledge rediscovery, architectural fragmentation, and reliance on great resources. So starting with knowledge rediscovery, agents tend to spend a lot of training time trying to rediscover strategies that are known to humans and known to prior models. There has been some work in trying to pre-train models, for instance, DQFD by Hester et al. In 2018. Although in that case, they also had to have a lot of human intervention, which is a bigger problem as well at scale when you're trying to scale reinforcement learning algorithms. So point 2, architectural fragmentation. A lot of these models tend to use LLMs tend to be used in a lot of these reinforcement learning algorithms as well, although they're used very sparsely in isolated cases. For instance, Voyager, which played Minecraft, tried to propose training scenarios for the reinforcement model to use, but it was very isolated in its usage. Finally, the reliance on great resource use, as explained prior, these models take a lot of time, a lot of resources to train. Therefore, there is this need for a sample efficient means in order to train. So again, with all this being said, existing models show that knowledge is useful, but they all fail to incorporate it as a structural component of reinforcement learning. So my position. To address these gaps, I propose framing reinforcement learning as a knowledge augmented process. Instead of relying solely on self-play, I want external knowledge accessed through large language models to be integrated directly into the training loop. in multiple different ways. This shifts knowledge from an auxiliary signal to a structured component of learning. So this is what I proposed. This is the model I made. On the left here, you can see a standard reinforcement learning loop where the environment feeds into the state, feeds into the agent. The agent produces an action. The action produces then a reward, and that feeds back into the environment that the agent then receives. In my model, I propose 3 different modes of implementing LLMs simultaneously. The first being reward shaping, which addresses credit assignment by providing more informative feedback. The second, goal suggestion, I should say in green, might not be very clear at the back of the room. It improves exploration by guiding the agent towards meaningful intermediate objectives. The third, curriculum generation in purple, top right, that structures the training distribution, ensuring the agent learns progressively. And together, these 3, they form a united framework that targets multiple bottlenecks simultaneously, rather than treating them in isolated cases. So, why does this approach fill the gaps? It fills it targeting the gaps directly. We can see that for the knowledge rediscovery, if we use knowledge augmentation, we can use LLMs to inject established strategy into the reinforcement learning process. So it doesn't have to reinvent the wheel in a way. For our second gap, we can use the united 3-channel framework in order to make sure LLMs have a say across the board of the reinforcement learning process. And I should also say it leads to a policy safe architecture, and I can talk about that if anyone has a question about that. And to answer the third point, we have sample efficient learning that replaces billions of brute force frames with guided exploration, making high-level reinforcement learning accessible on standard hardware.